Welcome back, Night Owls, and tonight we're figuring out how to integrate a sliced semicircle. The basic problem is this. Consider a semicircle centered at the origin of radius 5 with its diameter on the x-axis. If we make vertical cuts at y equals -3 and y equals +4, what is the area that remains? So in order to turn this into an integration problem, we first need to find y as a function of x to describe the curve of the semicircle. So if we say x squared plus y squared equals 25, right, obviously that would be the whole circle centered at the origin of radius 5. Y squared equals 25 minus x squared. Then we'll take y equals the positive square root of 25 minus x squared, right? Negative square root would get us the bottom semicircle. I guess in the problem statement didn't specify whether we wanted the top or bottom, but in all the images I have, I'm going to be using the top portion, the top semicircle. Obviously, the bottom semicircle has the same area. All right. So we would have to set up an integral of that, but it turns out before we get into that, there's actually kind of a low-tech, non-calculus way to divide the area. I was shown this actually by one of my calculus students back in my first year as a teaching assistant, where I was showing the, it was a calculus class, I was showing the generic calculus-based way of doing it, which had some tools that you're about to see that aren't immediately obvious. And one of my students pointed out that there's actually a way of explaining it with geometry. See, rather than thinking, well, I've got this semicircle and I have to vertically get rid of these slices, if instead you divide it diagonally like this, based on the geometry here, clearly these two triangles here are 3, 4, 5 right triangles, right? If I said radius is 5 and on the one hand I'm going out to 3, on the other hand I'm going over to 4, right? And if I look at these angles here, this line has slope -4/3. This one has slope +3/4. If two lines have slopes that are negative reciprocals of each other, they must be perpendicular to each other. Those lines are perpendicular. So they form a right angle, which means this is 1/4 of a circle radius 5. Whole circle radius 5 is pi r squared, pi 5 squared, 25 pi. Whole circle is 25 pi. Quarter of a circle is a quarter of that, 25 pi over 4. So the area is just 6 plus 6 plus 25 pi over 4, or 12 plus 25 pi over 4. But how would we do this with calculus? So for a more general case, we'd want, so we're going to integrate from -3 to 4. Our function is going to be square root of 25 minus x squared. Now, if instead of integrating my vertical strips as I move across at a constant horizontal rate, if my angle theta, where my angle theta corresponds to the angle in standard position of this line segment, if that angle is rotating at a constant rate, then how much area am I sweeping out? So the area I sweep out for any tiny little change in my angle is going to be the horizontal distance and times the vertical height. Horizontal distance is going to be my dx. Vertical height is going to be this 25 minus x, square root of 25 minus x squared. But in terms of theta, if my x is 5 cosine theta, right, in standard position, that's what it would be when the radius is 5. So x equals 5 cosine theta, dx equals -5 sine theta d theta. I forgot to put the d theta here, but we know it goes there. And so now when I do my substitution, getting my integral in terms of theta rather than x, my bounds also need to change. So if my bounds start from -3 and 4 in terms of x, then in terms of theta, that's inverse cosine of -3/5 and inverse cosine of 4/5, right? If x equals 5 cosine theta, then theta equals inverse cosine of x/5, right? Divide by 5, take the inverse cosine, and I've isolated theta. So what that means is I have integral from inverse cosine of -3/5 to inverse cosine of 4/5, and and my dx is this negative 5 sine theta d theta, and I put the negative out front so that it wouldn't look like I was doing a subtraction. I'm doing a multiplication by -1. And inside the square root, I have a 25 minus 25 cosine squared theta. Well, I can factor out that 25 from the square root to get a 5, and then my 1 minus cosine squared is just sine squared. Square root of sine squared is going to be absolute value of sine, but because my theta is always in quadrant 1 or quadrant 2, I don't need to worry about the absolute values. Oh, quick recap as to why I'm talking about absolute values. You might think, well, square root of sine squared, isn't that just sine? Typically, if it's square root of something squared, you need the absolute value of the thing you started with. Suppose I want square root of x squared. That's actually not x, that's absolute value of x. In the specific case, let's say, suppose x equals -3. -3 squared is 9. Square root of 9 is 3. I started with -3, I ended with +3. -3 is not 3. Absolute value of -3 is 3. So that's why, in general, you would need to worry about the absolute value signs, but because we're in quadrant 1 or quadrant 2, sine theta is always positive there anyway, so it is its own absolute value. With that technicality out of the way, we just combine all this to be integral from inverse cosine of -3/5 to inverse cosine of 4/5 of -25 sine squared theta d theta. How do we integrate that? Well, we use the relationship sine squared theta equals 1 minus cosine 2 theta over 2. Hopefully you remember that from Algebra 2. And with that substitution, this is clearly a nicer integral to work with, right? Because I can integrate cosine 2 theta relatively painlessly. All I have to do here is I pull out my -25 times 1/2. That gets me a -25 over 2 times theta. I get my cosine 2 theta, right? That becomes sine 2 theta over 2. Now, notice this over 2 comes out here. The over 2 down here comes from anti-differentiating cosine 2 theta. Right? When I do chain rule backwards, if I do chain rule forwards, I have to multiply by 2. For integration, I'm doing chain rule backwards, so I have to divide by this 2. That's why this 2 ends up down here. And so I get -25 over 2 times theta minus 2 sine theta cosine theta over 2. Right? Again, sine 2 theta equals 2 sine theta cosine theta. And I just have to plug in inverse cosine of 4/5 and inverse cosine of -3/5. So I notice that inverse cosine of 4/5 and inverse cosine of -3/5, those have to be off by pi over 2 from each other for the same geometric argument I made back earlier, where those lines clearly are at right angles. So this is going to end up getting you a pi over 2 when all is said and done. What about this 2 sine theta cosine theta? Well, cosine of an inverse cosine just gets you the original. Right? So cosine of inverse cosine of 4/5 just gets you 4/5. Cosine of inverse cosine of -3/5 just gets you -3/5. What about sine of an inverse cosine? For that, it helps to draw a little triangle. Suppose theta equals, let's say theta equals inverse cosine, theta equals inverse cosine of 4/5, right? So cosine theta equals 4/5. This triangle illustrates that. Clearly, by looking at the triangle, sine of theta is 3/5, right? Opposite divided by hypotenuse. So I can say that sine of inverse cosine of 4/5 is 3/5. And what about the one for -3/5, right? I can't draw a triangle with negative lengths, so I can't draw a triangle such that sine theta equals cosine theta equals -3/5, but I can use the fact that inverse cosine is an even function. So inverse cosine of -3/5 will be the same as inverse cosine of +3/5. And so I can use that to pretend that I'm looking at the 3/5 instead of a -3/5. So I get that sine of inverse cosine of -3/5 is +4/5. So I plug all those in. Right. Let's go back even. Right. So for 4/5, this becomes a 4/5, this becomes a 3/5. For negative 3 over 5, this becomes a negative 3 over 5, this becomes a 4 over 5. In one case, I get a positive 12 over 25. In the other case, I get a negative 12 over 25. And when the dust settles on all this, I get 25 pi over 4 plus 12, which is exactly what I was able to get doing it the geometry way. And so hopefully that motivates. The real key to doing this with a circle, or semicircle, is that when we did this trig substitution, typically they just say, do this trig substitution, trust me, it works. Don't ask where it comes from, somebody figured it out and it works. Here, it at least gives you a geometric motivation behind doing this trigonometric substitution. And for those of you who like explanations behind things, here's a way of explaining something that is typically just hand-waved and say, trust me, it works, you can verify that it works, don't ask where it comes from. As always, if you like my way of explaining things, found this informative, and wanted to arrange private lessons, click the link in the description, and until next time, this is Dr. Nighttime wishing you a good night.